As we are all familiar, the root 2 is an irrational number. But the question is how we can prove this statement. Yes, today's video is all about how we can prove this statement. Basically, we can prove the root 2 is an irrational number with the method of contradiction. Contradiction means to contradict or to oppose something. It is true that root 2 is an irrational number, but according to the method of contradiction, we just suppose for a moment that root 2 is not an irrational number but a rational number. Regarding the definition of rational number, we can put root 2 in the form of p by q, where both p and q are integers and q in the denominator is not equal to 0. Now, there is one important thing you should consider, that p by q is an irreducible fraction. This means there is no common factor between p and q other than 1. Let me give you some example of this to better understand this concept. Let we have a fraction 2 by 3. Now we can see there is no common factor. There is no common number between 2 and 3 that can divide both 2 and 3, but only 1 can divide both 2 and 3. Therefore, 2 by 3 is an irreducible fraction. So I hope now you better understand irreducible fraction. The next step is, now we will take the square of both sides of this equation to get rid of the square root. And after squaring, we will have 2 is equal to p square by q square. Now, we want to cancel this q square in the denominator, and for this purpose, we will multiply q square on both sides of equation, and after multiplication we will get 2q square is equal to p square, and that is our first equation. Now, there is also one more important concept to understand. So let's first consider, we know q is a member of integer. So if q is an integer, then its square would also be an integer. We also know that when we multiply an even integer with an integer, either it's odd or even, we always get an even integer. For example, when we multiply 2 by 5, then we get 10, that is even integer, and 5 is odd integer. And when we multiply 2 by 6, then we get 12, that is also an even integer. So this means when we multiply an even integer with an even integer or odd integer, we will always get an even integer. So we can say that p square is an even integer. So if p square is an even integer, then p square is divided by 2, as even integer is always divided by 2. So this is our statement that p square is divided by 2. Now we will use one theorem, and that theorem is, if any prime number divides the square of any number, then according to the theorem, that prime number will also divide the actual number. For example, if 2 divides the p square, as we said that p square is divided by 2, or 2 divides the p square, then the prime number 2 also divides p according to theorem. So this is our important statement to memorize. As we said that p is divided by 2, we can say that as a result of division of p by 2, we will get some integer. So we can say p by 2 is equal to c. Here c is some integer. And from this expression, we make this equation p is equal to 2c. Now the next step is, we will put p is equal to 2c in our first equation, that is p square is equal to 2q square. And after putting p is equal to 2c in this equation, we will get 2q square is equal to 4c square. Now we want to cancel out this q along q square, and for this purpose we will divide both side of equation by 2, and after division we get q square is equal to 2c square. Now you can see that this expression q square is equal to 2c square is similar to this expression p square is equal to 2q square. So this means q square is also an even integer, as c is some integer and it is multiplying by 2. Any number multiplying by 2 will always give an even integer. Any integer multiplying by 2 will always give even integers. So we can say that q square is an even integer and q square is divided by 2. Now we can say if 2 divides q square, then according to theorem 2 also divides q, as 2 is a prime number. So if any prime number divides the square of any number, then according to theorem that number, that prime number also divides the actual number, that is q in our case. So this is our second most important statement, that 2 also divides q. Now we have two important proofs. The first is 2 divides p and the second is 2 divides q. Now let's go back to the start of this lesson. At the start of this lesson we made a statement that this fraction p by q is an irreducible fraction, means there is no common factor between p and q other than 1. But at the end of this lesson we have proof that both p and q have a common factor of 2 other than 1. So guys, this is contradiction to our statement, means p by q is not an irreducible fraction as it also have a common factor of 2 other than 1. This means we cannot put root 2 in the form of p by q, and that is the definition of irrational number. Any number that cannot be put in the form of p by q is an irrational number. So hence proves that root 2 is an irrational number. So this is all about how we can prove that root 2 is an irrational number. Now at the end of this lesson I have an important question for you, as it is very easy for us that we can compare two simple numbers, like we can compare 5 and 3 easily, and we can also compare -3 and -4, and we can easily say that 5 is greater than 3 and -3 is greater than -4. But how we can compare two different rational numbers? So guys, there are three conditions of comparison of two rational numbers, and I will explain those conditions in my next video. Thank you.